All right, let's dive into the Floyd-Warshall algorithm. This is an incredibly powerful tool for figuring out the best way to get from anywhere to anywhere else.
So imagine this. You're not just looking for the best route from point A to point B. No, you need the absolute fastest route between every single pair of cities in an entire country. From A to B, A to C, A to D, then B to A, B to C, you got the idea. How would you even start to tackle a problem that massive?
Well, that's exactly what the Floyd-Warshall algorithm does. It's this beautifully elegant solution that finds the shortest path between all pairs of places in a network, and it does it all in one go.
So how on earth does it manage that? The secret sauce is something called dynamic programming. It's a really clever technique where you solve a giant problem by first solving a whole bunch of smaller, bite-sized pieces of it.
Now, this formula might look a little intense, but I promise you, the idea behind it is super simple. All it's doing is asking one basic question over and over. To get from city I to city J, which way is better? The route we already have, or a new potential route that goes from I through our new city K, and then from K on to J? The algorithm just looks at both options and keeps whichever one is shorter. That's it.
Here's how that plays out. First, we just map out the direct connections, the roads we know for sure. Then we introduce one city, let's call it city number 1, as a potential stopover, a middleman. We check if going through city 1 creates any new shortcuts between any two other cities. Then we do the same for city 2, then city 3, and we just keep doing that until we've considered every single city as a potential stopover.
And that's the simple question it just keeps asking. Each time we add a new city to the mix, we relax the distances in our map, which is just a fancy way of saying we update our map with any new shortcuts we just found. It's this step-by-step process of gradual improvement that lets the algorithm discover the absolute shortest paths.
Okay, so we get the core idea. Now let's pop the hood and look at the engine that makes this thing run. The how is actually beautiful in its simplicity, and it tells us a lot about how it performs. Believe it or not, that entire logic we just walked through, it's all driven by just 3 nested loops. The outer loop goes through K, that's our middleman city. The 2 inner loops just go through every possible starting point I and every possible destination J. That's the whole engine right there.
And because you have those 3 loops, each running n times for n cities, the time complexity is always O of n cubed, pronounced O of n cubed. It doesn't matter if it's the best case or the worst case. The algorithm is systematic, it checks everything, which makes its performance incredibly predictable.
And what about memory? Well, we need to store a distance for every pair of cities, right? That means we need an n by n grid, or matrix. So the space complexity is O(n) squared. And if you want to be able to actually trace the path later, you'll need a second n by n matrix for that too.
Okay, let's talk about something that can be a little tricky: negative numbers. Can you have a path that has a negative cost? You know, like a toll road that actually pays you to use it?
The short answer is yes, it can. And that's a huge advantage over some other algorithms like Dijkstra's. But, and this is a big but, there is one very important catch. And here is that critical distinction. A single negative edge, like that subsidized toll road, is totally fine. Floyd-Warshall handles that perfectly. The real problem is a negative cycle. That's a loop you can go around and around that actually ends up reducing your total travel cost each time. If you have one of those, you could just drive that loop forever to get an infinitely short path, and the whole idea of a shortest path just breaks down. So how do you spot one of these problem cycles? Well, this is where Floyd-Warshall is really clever. It has a built-in detector. After the algorithm is all done, you just check the cost of getting from any city back to itself. If that cost is a negative number, boom, you found a negative cycle. It's a super clear red flag.
So knowing all this, when is Floyd-Warshall actually the right tool for the job? Let's put it into context with some of the other players out there. Its real sweet spot is what we call dense graphs. Think of a network where almost every city is connected to almost every other city. Since its runtime depends on the number of cities, not the number of roads, it's super efficient in those kinds of highly interconnected maps. And, of course, you use it when you genuinely need the shortest path between all pairs, not just from one single starting point.
This table is basically your cheat sheet. If you're starting from just one place and there are no negative edges, Dijkstra's is your best friend. It's fast. If you have negative edges but still only one starting point, you'll want to use Bellman-Ford. But when you need all pairs, it's a showdown.
For those dense graphs we talked about, Floyd Warshall's simplicity and its O(n) cubed runtime often wins. For sparser graphs, Johnson's algorithm might be a better bet.
Okay, we've gone through a lot. Let's wrap this up and distill everything down to the most important things you need to remember.
So here it is in a nutshell. Floyd Warshall solves the all pairs shortest path problem. It uses dynamic programming by trying out every possible intermediate city. Its performance is super predictable, theta n cubed time and theta n squared space. And, crucially, it's cool with negative edges, but it's smart enough to flag those problematic negative cycles.
So here's your final task, your next step. Knowing the distance is great, but what about the actual path? Your challenge is to take this one step further. Go beyond just calculating the numbers and implement the logic to actually reconstruct the step-by-step route from any city to any other. That's the final piece of the puzzle to really mastering this algorithm.